So how many people went to lecture? How many people understood lecture?
What was the lecture?
Wait, what was the
Graphs.
Wait, oh my god, no, that made so much sense. Why?
Wait, the Rubik's Cube thing?
Yeah.
I guess.
Wait,
Yeah.
that was like really simple.
How long did you talk for on Rubik's Cubes?
For a while.
So we talked a little bit about Rubik's Cube, and then we talked about graphs and breadth first search, which you can use to solve Rubik's Cubes.
Is that what we're talking about today?
Is that,
About that?
were you passed out by the time we got to graphs? Okay.
I talked about my Rubik's Cubes.
Okay. All right. Well, so I want to talk about two things, maybe depending on the level of interest. We can talk a little bit about P-set 5 and the things that I think are weird in the coding part of P-set 5. And by the way, how many people started P-set 5?
I downloaded it.
Maybe we're not going to talk about P-set 5. You guys need to start early. You did. Yeah. Yeah, I guess I can't punish you for everyone else. So P-set 5, and I can talk about graphs. I can talk about whatever didn't make sense in class, and I can talk about background stuff for graphs. So how do people feel? Who wants to talk about the P-set that we haven't read? Who wants to talk about graphs?
We took 6042.
Yeah, if you took 6042, nothing here is new. I mean, nothing in the recitation is new. We're going to take you to new heights of graph knowledge, and you'll be able to do many more cool things that you're able to do before. Okay, so P-set. For people who started early, what's the gist of the coding assignment?
So you have to speed up something. When I ran the tests, do I say what I got as my results?
I mean, the time isn't on the P-set, so you can say what you got as a
Pardon?
time. The time isn't on the P-set, so you can say what you got as a time.
Okay, well, so the slowest thing was like add for me.
Okay. Well, you should look to see if add is a valid answer. Look at the questions and see if add is a valid answer.
Okay. All right. Wait. Okay.
It's not like what's the slowest function, right? There's more text there. So you should
Right.
read the rest of the text and see if add makes sense as a valid answer.
Sure. Okay.
Okay. So what you're doing, big picture, is you have some processor that's not a real processor. And it can do arithmetic with bytes and 16-bit words. And we give you the basic operations, and then we give you a library for large number arithmetic. Because guess what? 16-byte addition, subtraction, not going to cut it for, I don't know, science applications or for cryptography, what we want you to play with. So let's see, what are the basic operations that that processor can do? Front of the P-set, so even if you didn't get to the coding assignment, you can still tell me.
Zeros, I think.
Okay, so plus, minus, multiply, divide, and mod. Let's start with these. So you have two primitives in that processor, right? You have bytes, which are basically 8-bit digits. So there's 200, the range is 0 to 256, and words. And the word is 16-bit from 0 to the 16 minus 1. If you care to know, this is 65535. Okay, so if you take 2 bytes and add them together, what do you get? Not quite. It's a trick question. You get a word. So the processor cannot do simple math on bytes. It converts them up to words, and all the math happens on words. Now, if you get 2 words and add them up together, what do you get?
2 words.
You'd wish we're not that nice.
A word and a carry bit.
Sorry, you just get a word. At least nobody said a byte. I was like, please don't say byte. Please don't say byte. So you said carry bit. Why do we care about the carry bit? What's the problem if you do addition this way?
If you're going too high, if the highest bit is 1 on both of them, then it's like overflow kind of.
Yep. So suppose we're trying to add 2 to the 16 minus 1 plus 2 to the 16 minus 1. By the way, does anyone remember hex notation, hexadecimal? OK, people who studied the PSET remember. That's good. So it'll be easy to write things in hex for the PSET. So if you try to add these numbers, you're going to get 1 F, 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 E. And you can use the math here to see that this is more than a word. So you would like to know that this thing overflows, right? You'd like to know that there's, well, we don't give you that. So all you get is this. So addition happens modulo 2 to the 16. If you want to be able to detect overflow, what do you have to do?
Just test those bits.
Test. OK, that's one way of doing it. It would take quite a few instructions, though. So if you want to do overflow detection, the easiest way, I think, of doing it is to use this form. So suppose you have 2 bytes. This is the maximum value in a byte, right? 255, 2 to the 8 minus 1. If you have 2 bytes and you add them all together, you're going to get 1 FE. Right? So it's just like the case here, except you have fewer Fs. OK, where's the carry here?
It'd be the 1, right?
Yep. So this guy here is the carry, and this guy is the low result. OK, does anyone know how these are called? If you have a word and you have 2 bytes, what's the first byte, what's the second byte? All right. So most significant byte, MSB, and least significant byte, LSB. So if you want to figure out your carries, then you should do your math this way. You're going to have byte 1 plus byte 2, add them together, and then you call LSB to get the byte result. And then you call MSB to get the carry. So this is addition. Everyone with me so far? By the way, are these numbers signed or unsigned? No negative numbers, right? So no support for negative numbers. Everything is going to be positive. And we're going to build everything we need off of positive numbers because they're easier to deal with. What if I have 2 words and I subtract them? What do I get? OK. What if I have 0 minus 1? What do I get? 0. Not quite.
Like, if you're not using sign?
Oh, do you get like
Oh, you got
ones?
1.
All ones, OK.
Yeah. Wait.
So all ones would be this. F, 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 F.
But that's assuming that it's signed then. Or that it's
No,
just complement.
it's just
Well,
it'll
It's just
overflow.
complement, yeah. Oh, okay.
So that's a really big number.
OK, so fancy CS, choose complement. For people who think in math mode, what is this?
Big.
It's minus 1 mod 2 to the 16. So remember when we were doing modular arithmetic before to figure out a number's multiplicative inverse? And when we were doing rolling hashes? We didn't want negative numbers, we made them positive. So minus 1 mod 2 to the 16 is 2 to the 16 minus 1, and it comes out to this value. So you get minus 1, it's just that you have to know your basis. Okay, so we got addition and subtraction. Let's talk about multiplication. What do you do for multiplication? What can you multiply? 2 bytes. Very good. Just 2 bytes. What do you get? A word. Thank you. So you multiply 2 bytes, you get a word. What if there's overflow? No, it's a trick question.
There's no overflow.
There is no overflow. So 2 bytes, 2 to the 8 minus 1 times 2 to the 8 minus 1 is 2 to the 16 minus 2 to the 8 minus 2 to the 8 plus 1. So this is smaller than... You can say this safely without doing the arithmetic, right? So this is how much you can hold in a word. This is how much you can hold in a byte. So,
why do minus 1?
yeah, minus 1. Well, there's a minus 1 here, there's a minus 1 here, but I can't find it here, so roughly this. But there is no overflow.
Like, where'd you get the minus 1 from?
Where do you get the... So this is how much you can hold in a byte. So a byte has 8 bits, right? From 0, 0 to FF. So this is 2 to the 8 minus 1. Okay, so multiplication, there is no overflow. I don't have to deal with that. You guys have to figure out how to deal with it. How about division? What can you divide?
Words.
Almost. A word divided by a byte. Do we have, what do you get out of it? That would be nice. Nope. Sorry, you get a byte. And if you do modulo, you also get a byte. What if there's overflow in the division? What happens? What would you expect to happen?
We don't have any like floating point numbers, so we shouldn't get overflow, right?
How about 2 to the 16 minus 1 divided by 1? So what do you get?
Same thing.
Will this fit in a byte?
Yeah. No. No.
Okay.
Oh, that can have overflow.
Yep.
You get a word.
You don't get a word. I promise you get a byte. So what will that byte be?
The wrong. No, wait. Oh, it's going to be modulo something. It's going to be.
That's reasonable, right? Modulo to 56, because that's what it can carry. Okay, what about modulo? What happens there if you get overflow?
It's just gonna loop, right?
Same thing.
0.
So if you do a modulo, this is going to be at most 255, right? If you do modulo 255, the remainder is going to be between 0 and 254. Will that ever overflow a byte? So no overflow. No need to worry about it. So word addition can overflow, subtraction can overflow, multiplication doesn't overflow, division overflows, modulo doesn't.
By overflow, you mean like will exceed the space of the byte, right?
Yes, it exceeds the space of the result. Because here, if you're adding 2 words, the result exceeds the space of a word, which is what you get.
So is it just, in all cases, it's just truncated?
Yep, pretty much. Exactly. So the reason you have to deal with this weird system is this is pretty much how Intel does their arithmetic. So if you look at old school 16-bit Intel processors, you have registers and you have exactly these operations. For newer processors, they're 32 bits, but then it's just you write more Fs on the board and you get the same thing.
Is it most significant bit or most significant byte?
Most significant byte. On a real processor, you have registers that are the size of a word, and then you can pull out the bytes in constant time. So what constants do we have? These are the operations. What constants do we have? Only two constants. 0 and 1. What if you want to get something bigger? What if you want to get 2? How do you get 2?
And 2 ones?
Yep. What if you want to get this number?
Do that several times.
It's kind of painful to type, even if you copy paste. So there's a method on Word called from bytes, and it takes an MSB and an LSB, and it gives you a word. So what would I give it? Let's give it a 1, and let's give it a 0. So this will get 1, 0, 0, and then minus 1. Yes? Okay. So Intel is pretty nice about constants, but some other processors aren't, so I figured, why not? Let's get you acquainted to these kind of tricks too. Let's make the piece more interesting. All right, so any question on this fake processor that you'll have to code for?
Can you explain the last one again?
Here?
Yeah, word from bytes.
So word from bytes, a word is 2 bytes, one next to the other. Give it the first byte, give it the second byte. In this case, the first byte is 1, the second byte is 0. All right, so 2 bytes, a 1 and a 0. How do you write this in hex? 1, 0, 0. 1 byte, second byte. And then I subtract 1, and I get this. Okay. So while I erase the board, I want you guys to think of graph questions, because this is the other topic we're looking at today. So what was unclear about the lecture? What is unclear about graphs in general? Do you guys remember the handshaking lemma? What does it mean? How do you prove it? Things of that sort. So what do you guys want to cover today?
Handshaking, that's the thing where if you have a bunch of nodes and they're all connected, well, I mean, like, they're all in a graph, in a closed graph, that the number of edges is equal to twice the number of vertices.
Okay.
That's all it is, right?
Twice the number of vertices?
The number of handshakes
No.
that occurred are twice the number of edges.
Yeah, wait.
You said the number of vertices. Well, wait.
Oh, yeah, that's right.
No, vertices and
No.
edges are not related
No,
in a
no,
graph.
no.
Yeah, think of a triangle, right? That's 3 edges, 3 vertices,
Yeah.
which is like not 2 times, which is what you said.
Oh.
It's the number of degrees is twice the number of edges.
Oh, that's what I was thinking.
Yeah.
All right, so let's start with simple stuff. What's a graph?
Nodes and edges.
All right, fancy word for nodes. Vertex, vertices and edges. How do I draw vertices? How do I draw edges?
Circles.
Circles and lines.
Certain ones.
Possibly arrows.
Possibly arrows, I like that. You want to get fancy. All right, so when do I draw an edge as a line? When do I draw it as an arrow?
Directed under.
Which one's which?
Directed as an arrow.
Directed under.
Cool. Let's draw this graph here. Yeah, it looks like a pretty boring graph. So, is this graph connected or not?
Yeah.
Okay, what's a connected graph?
Any node can get to any other node following some path.
There's a path from any node to any other node. Okay. So how do I make this unconnected using the least amount of effort? It's a bit of a trick question. So any guess is fine.
What was the question again?
How do I make this unconnected using the least amount of effort on my behalf?
Just add a node.
Okay, I heard remove edges. I don't like erasing because I don't like the...
Oh no, Kratos.
So.
Yeah, just add a node.
Oh.
Yep, so I like that answer out of the two I heard. So now it's not a connected graph. How many connected components does it have?
5.
Two
Or,
connected.
2 and 5.
well, one connected component, but there are 2 components, maybe.
Okay, what's a connected component?
It's like that part of the graph is the like follows the properties of being connected. So there are like 2 parts in this graph. That's why we say there are 2 connected components.
So connected component is a bunch of vertices such that you can get from one vertex to all the other vertices. And that's true for, if the graph is undirected, that's true for any vertex in the set. And we also want that set to be maximal, because if we say this is a connected component, it's not very useful. Noticing that this whole thing is a connected component, useful. So this is one component, this is the other component. Make sense? So we have the world, we have cities. You can bike from a city to another city, and that's it. No other route of transportation. How many connected components?
7?
Okay, roughly 7.
I mean, assuming
Why?
anyone lives in, the South Pole. But
Okay, so what are these 7?
7 continents?
Okay,
Do I know all of them?
let's say roughly 7. So this is what I wanted. I wanted some thinking. So if you try to get from a continent to another continent, presumably you'd go through some patch of sea, because otherwise why are they calling them continents? Okay. Does anyone want to give out another answer? Asked this in the previous section, and some people there gave me some very precise answers that are not continents. This is what I had in mind, by the way. So
Okay, good.
as far as I'm concerned, this is a good answer. Come on, guys. World. So 2 things. Islands
Oh.
Oh.
and Europe and Asia are connected, so you can go from one to the other, right? They're weird. Why are they separate continents? No idea. The geography people might.
Are there like walls between or something? Yeah, there's.
Sorry?
The Ural Mountains? I guess you could bike through that.
Okay, so it would be a pain to bike through that, but presumably you can. If you have a robot that doesn't get tired or something, you can bike.
Doesn't mind falling off cliffs.
Okay, so the answer, depending on how much geography you know, is somewhere between 7 and 10,000, I guess, or whatever the number of islands is. There are a lot of tiny islands somewhere, right? Anyway, it's between 7 and a big number. So these are connected components in the world. What's the degree of A? 2. What's the degree of D? Very good. Let's make this. The degrees of FGH, 2, 2, 2. The degree of C, 2. The degree of B, thank you. And the degree of E. Okay, if you add up all these numbers together, what do you get? I can't do math, so I couldn't possibly have added all these numbers together, right? I used something else. How many edges do I have in the graph? 1, 2, 3, 4, 5, 6, 7, 8, 9. See a connection here?
Yeah.
So this is the handshaking lemma. That's all there's to it. So if you look at the degrees of a node, each edge adds 1 to 2 degrees. For instance, this edge adds 1 to C's degree and adds 1 to D's degree. If you're a math person and you write this up, you have to write sums. And you have big sums of using intimidating notation. So it's not as obvious. But this is really all there's to it. Each edge contributes 1 to 2 nodes degrees. So if you add up all the degrees, you're going to get 2 times the number of edges. So far, so good? OK, what if we have directed graphs? What if I had this? How did I draw this? A, B, C, D, E, F. What is the degree of A? Not quite. Sorry, that was a trick question. A doesn't have a degree. So if you have directed graphs, you don't have degrees. You have in degrees and out degrees. So now that I've said that, you know what they are, right? What's the out degree of A? Sometimes this is known as the degree of edges. So this is 2. And what's the in degree of A? All right. So A has 2 edges going out, 0 edges going in. How about D? What's the out degree of D? Come on, guys. Don't scare me. And what's the in degree of D? 2. Very good. So what's the equivalent of the handshaking lemma on oriented graphs?
Some of the in degrees and out degrees.
OK, what about them?
They're equal to twice the number of vertices.
Not
No.
quite. They're equal to... You had 80% of the answer.
Oh.
So the sum of the in degrees and
Yeah.
the sum of the out degrees.
Add them up.
But if you add them up, you will get 2 times the number of edges. That is
Oh.
correct. But I want something more...
They equal each other?
Yep, that's a bit... Yeah. This is cooler, right?
Okay.
So why is that? Does anyone see why that's the case? Each edge come on, guys. So what does each edge do? All right, so if I look at this edge here, this edge is going to contribute 1 to B's out degree and 1 to D's in degree. So each edge contributes 1 to an out degree and 1 to an in degree. So that means that total sum of out degrees equals the total sum of in degrees, and both of them are E, and them combined to E. Sorry, I don't know why that didn't click to me right away. OK, so the intuition behind this is that for every node, if you take an edge, you're going to get somewhere else. If the sum of the out degrees was bigger, then you have a black hole somewhere. You go on an edge, you don't come back. Same for in degrees. OK, how do we represent graphs?
You just did.
So sure, if we're drawing them on the board, that's what we do. But if you're in Python, what do you do?
Oh, you can have a linked list, right? Of each node having its neighbors as it linked to it.
OK, so I have one big linked list. Or how does this work?
Well, I guess you'd have like a starting point of some sort, a starting node, and then from that node you can have its neighbors connected to it. as like,
Okay.
it's not really
So-
linked list, I guess.
So I wasn't precise. That is not trivial to build. By the time we build that, we're done with this recitation. So what you get is the vertices and the edges. And we want an easy representation that just looks at the vertices, builds something, looks at the edges, builds something.
I guess you have a table of values. Like A has these neighbors.
Okay.
Dictionary.
Let's go for that. So we have a dictionary, and for each node you have the list, each vertex you have the list of vertices that are connected to it. So what's the list for A?
B and C.
Okay, what's the list for B?
A, D, and E. Etc.
All right, so in Python, would be a dictionary, right? So how much total space does this take? Number of?
Well, then there's also the space for each of the lists, though.
Okay, so if these were actual slots in an array, so if this would be an array, I would have the number of nodes. You're giving away the answer to my next question. So I have V slots here. So if this would be an array, it's order V just to store this. The thing in Python is that you have these dictionaries that are fancy hashes where they grow as you need them. So if, for example, you have 10,000 vertices, but you don't have any edge, your dictionary size is going to be order 1, because it only grows as you add edges to it. So this is assuming that I don't store empty lists. So if I have a stray node here, if I have a node I, say this is I, if I don't store anything, I don't have to pay for it. If I store an empty list here, then I have to pay for it. And there's an order V component that you mentioned.
So like, let's say if there's a graph where everything is not connected, so there are like a bunch of vertices, then in that case it would be order V, right?
It's order V if we store empty lists for the nodes that don't have edges.
Right, and if none of the nodes have edges, like they are all unconnected.
Yeah.
Then
On the other hand, if I don't store anything for the nodes that don't have edges, it's order 1.
Okay.
Okay, so
if we get like no edges, do we do like empty list or do we not store anything?
depends on what you want.
Okay.
So if we store empty lists, you're going to have an order V cost here, but your code is going to be simpler, presumably, because you don't have to check if something is or isn't in the dictionary. Okay, how about this stuff? What's the total size of this stuff here? Okay, order E. How many elements do I have in here in total?
In the
In this thing here. So what's the sum of the length of the lists?
average value of E times the number of vertices.
Let's go for something else. All right, that's what I wanted to hear.
Oh.
So A lists its neighbors, right? The number of neighbors that A has is the degree of A. B lists its neighbors, so this is the degree of B. So if you sum up over all of them, what's the sum of all the degrees in the graph? 2E. We learned about this, right? Handshaking lemma, 2E. So what is the total cost for storing this data structure? So V plus E, assuming empty lists. Okay, let's look at another data structure for storing things in a graph. So instead of using lists, let's use a matrix. A, B, C, D, E on top. A, B, C, D, E on the left. Let's pretend our graph is just that component over there, because otherwise it just gets big and there's no extra insight. So does anyone know how this is called? If I put numbers here, does anyone know what this is called?
Not a matrix.
There's a fancy name for it. It ends with matrix. Okay.
Two-dimensional array.
I don't think we taught it to you, so don't worry. The fancy name is adjacent. Maybe it's misspelled, but it's something that looks and sounds like this. Adjacency matrix. Misspelled? Okay. I hope someone will help me. Okay, so if this is an adjacency matrix, what should this element tell me between B and A? Yep. If it's an adjacency matrix, it would better tell me if they're adjacent, and they're adjacent if they have an edge between them. So for A and B, what does it happen to be?
1.
Okay. A and A, what do we do?
0. Well, 1. It's adjacent to itself.
What's easier for the algorithm that you're trying to implement?
1.
So it doesn't really matter. We use ones most of the time, but sometimes it's easier to use a 0 than use a 0.
And you can get to A from A, right?
Yeah. So that's why you'd use a 1. Sometimes, though, you don't want to in code. So between A and C, so someone dictate this to me. Or everyone dictate this to me so I know it makes sense. So A and C, is there an edge between them?
Yes.
Yes.
What do I write?
1.
A and D.
No.
No.
2.
A and D.
2.
BA.
1.
BC.
0.
BD.
1.
BE.
1.
Okay. CA.
1.
CB.
2.
CD. CE. All right. Now I'm gonna use the bits you gave me to come to get this. See if I can do it correctly. And D. I'm not looking at the graph, by the way. I'm trusting you, so better give me the right answer. D. And DD 1. Okay, how many ones do I have in this? To see if you guys are thinking.
2E.
So each edge contributes to 2 ones, right? And that accounts for most of the ones.
Oh, plus B.
So this is how many ones I have. How many zeros do I have?
B squared minus 2B plus 1.
So this is a non-boring way of asking how many elements I have in this matrix. This is what I was looking for. So V columns, right? V rows, V squared total elements. So how much memory do I need to store this?
Squared.
V squared what? If I want to store it as compactly as possible. So I want to pack these as tight as I can.
I mean, you need the entire array, right?
Yeah, so what do I store? V squared what?
Oh, you mean units?
Yeah, what's the unit?
Oh, 1 bit.
All right, so V squared
Bits?
bits. Whereas this is V plus E words, because you have to store pointers everywhere here. So sometimes if your graph is really dense, you might prefer this representation. Let me see how much time do I have. Oh, plenty of time. Who remembers breadth first search? Yes.
Basically, you just start at some node and you just check all its neighbors and check all of those neighbors and then check, yeah.
All right. So breadth first search, we have a graph. So suppose this is our graph, and I do a breadth first search starting at A. How does that work? So I start out with a list of the nodes that I'm going to visit. I initialize it with A because this is the only node that I know about. What happens next? All right, so I take out of the list the first thing that I can. This is my current node. You said I visit B and C because they're the neighbors, right? So I took A out of the list. So A was definitely visited, and I'm visiting B and C. What do I do when I visit them? Put them in a list. So this means I discovered them, and I'm going to visit them later. So I discovered them, I know of their existence. What happens next?
Check if B is what you want.
Okay, so B gets out of the list, and what do I do?
Or discover its neighbors.
All right, so his neighbors are A, D, and E. What now?
If they haven't already been in that list, then add them otherwise.
Okay, A was already visited, D and D weren't. So D and E, then what happens?
C's and
Any neighbors that I haven't seen? Nope. Then E and okay, and then
I guess you could go to F, but it's not connected to anything. But I mean, well, how did you get to A then, right? Like,
so A is the first node. I started with A because I said I'm doing a breadth first search starting from A.
okay, well then you.
So
have
BFS starts from somewhere. A BFS has a source. And we'll see why that matters in a bit. So do I ever get to CF? Nope. So if I start at A, what are the nodes that I visit and what are the nodes that I don't visit?
Well, you visit all the ones in the connected graph.
All right, in the connected component. So the whole graph can be connected or not connected. So the nodes that I visit are the nodes in A's connected component, because by definition, those are the nodes that I can reach from A. So if I have many connected components and I use BFS starting from one node, I might not visit the entire graph. How do I keep track of what node I've discovered and what I haven't discovered? So what data structure do I use for these smiley faces? So for the smiley faces. For this thing, I probably want a queue. We teach you something simpler, but most of the time when you write the code, you actually use a queue. But what do I want for the smiley faces? So when I pull a node out, say I pulled out B, and I see ADE, and I want to know that I visited A and I didn't visit D and E. You guys remember that we didn't visit D and E, right, by the time we got to... OK. So I want to be able to check whether I visited a node or not really fast. So what data structure should I use for the smileys? A hash table. Cool. What's a hash table in Python? Dictionary. All right. So this is going to be a scene, which is a dictionary, and it maps vertices to maybe true. Yep. Yeah, Python has a set, right? So yeah, you can use that. Okay, so this needs, the smileys need to be some sort of smiley. Needs to be some sort of dictionary. So given that, and assuming that this is a queue that we can extract and insert from in constant time, what's the running time of BFS? Let's make life easy. Let's assume the graph is connected. So let's assume this doesn't exist. So BFS, what's the running time? So you visit every node once, so it's at least V. That's a start. Now what do you do when you visit a node?
Check all the...
All the neighbors, right?
Yeah, also.
So given the node, you have to go to the data structure that you have. That's either this or this. And you have to get a list of neighbors. If I have this data structure, how fast do I get a list of neighbors for a node?
Order degree.
Yep, order of the degree of the node. That's good. How about this data structure?
Same. Oh no, that's order V.
Yep. So in this data structure, for example, C only has two edges coming out of it. Sorry, because this is also. But I have to go through the entire line in the matrix to see where I have my zeros and where I have my ones. So in order to list the neighbors, here, this is straight up order V, whereas this is order of the degree of the node that I'm looking for. So for this, where it's nice and simple order V, what's the total running time?
Right, because it's b plus b. Oh no. Leave one.
So for each node, I have to.
B squared.
Okay. So we're up to V squared already. And what else do we need to do? Anything that we need to do on a node is order V. So V squared is going to be the total running time. That's it. So if we use adjacency list, an adjacency matrix, we get order of V squared as the total running time. What about if we use lists? What's the running time? I'll give you a hint. You have to use amortized analysis. Shivers anyone? So we know it's order V because we're going to visit every node. And you guys didn't see what I was going to write here. Okay, so for every node, I go through the neighbors and I do something to them. Right? I check if they're in scene, and if not, I add them and I add them to the list. So for every node, the work is?
Or is degrees.
Yep. So if I look at all the nodes,
It's E.
yep. So for every node, I have to look at its neighbors, and I have to see which neighbors are in scene, and for the neighbors that are not in scene, I have to add them to my queue. So checking if a neighbor is in scene or not, order 1. Adding it to the queue, order 1. So the total work for a node is order of neighbors because of the adjacency list, not matrix. If I look at the entire graph, here I can't do a local analysis like I did before. If I look at the entire graph and I look at all the nodes / vertices, then the total work is the sum of their degrees. For each node is degree, total work, sum of the degrees. And I have that nice handshaking lemma that says that the sum of the degrees is 2e, so order E. So total running time, V plus E. Okay, can I say the running time is order E? No V's?
No, because you have to look at every word.
Well, the e is greater than that, right?
Is it?
We greater than n, right? In case of like not connected components,
But you have to look at
we would
those.
have less, but we would have.
We're not gonna look at them. We look at us.
Oh yeah. True.
I mean, you could.
But then.
It's possible that you get more vertices and edges, so you can't just say,
Okay, so it's possible that I have more vertices than edges. I agree with that, but do I do anything to the vertices that I haven't seen? So this is subtle. The difference between this and this is a matter of how you implement everything. In CLRS, they assume that this scene is an array. So all their nodes have numbers from 1 to v. So then they initialize an array, everything is false, and then they set the true elements. In Python, we can use a dictionary and not initialize it with anything. So if you do it that way in Python, if you code carefully, you can get to order E, because the parts of the graph that you don't discover, you don't have to pay for them. If you look at CLRS code, it's definitely V plus E. So the difference between this and this, it depends on the code. What's the point of BFS, by the way? Why do we care? What does it give us?
Shortest path
From shortest path from point.
like from
Okay, so it gives me the shortest path from the node that I'm starting the BFS from. So only from this node. So it's going to give me, if I start my BFS at A, it's going to give me the length of the shortest path from A to which node? All the nodes. All the nodes that are visited by BFS are reachable, and we have a path from them. How do we compute this distance? Let's see. So what's the distance from A to A? 0. When I start from A and I see that its neighbors are B and C, what's the distance from A to B and from A to C? Okay, now I look at B. What's the distance between A and A? A is B's neighbor.
A and A.
Yeah. So I have 3 neighbors. B has 3 neighbors, A, D, and E. So I care about the distances between A and ADE. Distance AA, distance AD, distance AE. So this one's 0. How about the distances between A and D and A and E? They're 2. So the way I would compute these distances is I start with A being 0, the distance from A to A is 0. And then when I look at the node, when I discover the neighbors, all the neighbors that don't have smiley faces on them get the node's distance plus 1. Because you can get to them by getting at the current node and then traversing an edge. When you do that, it's important that you don't update the distances of the nodes that have smiley faces. Because if you do, you're going to say that the distance from A to A is 2. And all hell breaks loose from there.
Wait, why would you say it would be 2?
If I forget the fact that it has a smiley face. So if I go through all of B's neighbors and I say the distance from A to B is 1, so the distance from A to all of B's neighbors has to be 2. That would be wrong.
Wait, from A to all of
B's neighbors.
From A to all of B. Oh, because A is one of
These neighbors.
Yeah,
Yep.
okay.
So the smileys tell me which vertices I've already seen, and I've already presumably computed distances for them. So we don't want to update those. Okay, this is BFS in essence. One question. Facebook and Twitter, which one's directed, which one's undirected?
Facebook is undirected.
Okay, Facebook. Undirected. Why is it undirected?
Oh, because they're supposed to be friends with someone, or they're supposed to be.
Okay, so
So if you can follow someone, they don't necessarily follow you.
okay, so this is Twitter, right?
Yeah.
Twitter directed because of follows. Has anyone used Facebook recently? Did you guys see there's a new option?
The little scroll bar on the side.
That is subscribers.
Oh, yeah.
Do you know-
that thing.
Okay, so how do subscribers work?
You subscribe.
It's like Google Plus.
Yeah.
Okay, directed or undirected? If I subscribe to you, do you have to subscribe to me?
Directed.
Directed.
So which one is it?
Facebook is kind of directed now, because you can unsubscribe from people.
Is it? So Facebook has 2 graphs in it. They happen to have the same vertices. The people are the vertices in both graphs. But the friends relationship defines an undirected graph. The subscribers relationship defines a directed graph. The graphs are completely different. And there are 2 graphs. That's the right way to reason about them. That's why it was slightly tricky. Okay, can someone think of a cool way to use BFS on Facebook?
And it's networks, right? Like figuring out how many people are in the first degree or second degree.
Okay,
MySpace was really into that.
LinkedIn also does that, right? So how many people are your friends? How many people are your friends' friends? So on and so forth. Okay, now suppose you want to get to someone in Facebook. and you don't know them directly. They're not your friends. Presumably, you want to get to them through the minimum amount of effort. So you want to see what's the, do you have a friend that knows them? If not, do you have a friend that knows a friend that knows them? Do you have a friend that knows a friend that knows a friend that knows them? So on and so forth. So BFS will give you that minimum path. Okay, do graphs make sense? So by the way, BFS on Facebook is just the beginning of a ton of cool things you can do with graph algorithms. Okay, I was hoping it would get people excited, but I see you guys are kind of looking forward to partying for the weekend. So any questions before that? Okay, enjoy the pizza then.
Partying on the weekend.
Yeah.